Today's notes are on scientific notation. Notation is how we write or identify something, and scientific is just pertaining to science. So this is how we are writing things in scientific terms. The reason it's scientific is because in science, a lot of times you're looking at things that are either really small, such as bacteria or single-cell organisms, or really large, such as planets or stars, galaxies, things like that. So it's hard to use numbers that we would normally use. In the case of the really, really small object, you end up with things like this is 1/100,000th million thousandth of a gram, or this is 100 million light years away. So instead, we use scientific notation to indicate the need for all of these place values, for all of these zeros. This is our format for writing in scientific notation. First, we start with a number that's between 1 and 10. Now that number can be 1, but that number can't be 10 because 10 has 2 digits. So it could be 1.9, it could be 1.986, it could even be 9.9 repeating, but it cannot get all the way up to 10. Then we multiply that by 10 to some power, and the power has to be in the form of an integer. So it could be positive integers or whole numbers like 2, 10, 23 even, or it could be a negative integer like -2 or -10. Here's some examples of numbers that we've seen before being written in scientific notation. For example, the number of stars in the Milky Way is 200 billion, but instead of writing 9, 10, 11 zeros, we say there are 2 times 10 to the 11th power stars in the Milky Way. Or the weight of an electron. You could write out this entire long thing. I don't even know how to read that number. Or you can express it as 9 times 10 to the -31 power kilograms. See, math is all about problem solving and efficiency. And a problem that we have is we actually have to calculate things using these really long numbers, and we needed a more efficient way to do it. So scientific notation helps us to solve problems with very, very large and very, very small numbers. If we're going to be writing in scientific notation, we need to understand how the powers of 10 work. There's a couple of gimmies, ones that we've seen before. 10 to the 0 power is just 1 because anything to the 0 power is 1. And 10 to the first power is 10 because it's not going to be multiplied by anything. But 10 squared is 10 multiplied by 10, which gives us 100. 10 to the third power is 10 multiplied by itself 3 times, which gives us 1,000, and so forth and so on. When you get into negative exponents, those are indicating that that is the denominator. So 10 to the -1 power is really 1 over 10 to the first power, which gives us 1/10. 10 to the -2 power is 1 over 10 to the second power, or 1 over 10 times 10, which is 1/100th. And the pattern continues all the way to 10 to the -5th power, or 1 over 10 to the 5th power. All of these get multiplied by some number between 1 and 10. For example, 4 times 10 to the 4th power would be 4 times 10,000. Or 4 times 10 to the -4th power would be 4, and then I move my decimal 1, 2, 3, 4 places since I'm dividing, and I get 4 10,000ths. When it comes time for us to write numbers in scientific notation, we're going to count our decimal places to get it to a number between 1 and 10, because when we move decimals forwards and backwards, it indicates that we're dividing and multiplying by 10. Looking at example 1, this decimal has to be moved twice in order to make this 5 4/10, which is a number between 1 and 10. Since it moved twice, it's 10 to the second power. But remember, this is a number that is smaller than 1, which means that in order to get that decimal place here to give us that really small number, it's 10 to the negative second power. For example 2, we're writing 86 trillion in scientific notation. So how many decimal places does it take for us to get to a number between 1 and 10? Well, I have to move it 3, 6, 9, 12, 13 places. So in scientific notation, I have 8 6/10 multiplied by 10 to the 13th power. When it comes to expressing in standard notation, we follow those same patterns. I start with 5 4/10, but that decimal has to move 3 places to the right since it's being multiplied by 10 3 times. So that's 1, 2, 3. And we fill in with zeros. That gives me 5,400 in standard notation. And for our second problem, we have 10 to a negative exponent. So I start with my number of 8 13,000ths. But this time, since I'm multiplying by 10 to a negative exponent to the negative 6th power, remember that means it's being multiplied by 1 over 10 to the 6th power. So the decimal is actually going to move to the left to make this a very small number. And it moves 6 times. 1, 2, 3, 4, 5, 6. And I fill in all of those placeholders with 0. So my final answer would be 8,013 billionths. Here are 2 problems for you to try. You don't have to copy them into your notebook, but you do need to write the correct answers down. It might actually help to write the numbers so that you can count your decimal places like we just practiced. Ready? Expressing in scientific notation, 245,600,000,000. I count my decimal places to get this to be a number between 1 and 10, so I need 1 digit in front of the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. That gives me 2.456 times 10 to the 11th power. And I know that my power is positive because this is such a large number. It had to be multiplied by 10 over and over and over. For our second part, expressing in standard notation, one with a negative exponent. So I start here and I move the exponent -3 places. 1, 2, 3. Because when I multiply by 10 to the -3rd power, I'm multiplying by 1 over 10 times 10 times 10. Or you could see it as dividing 10 3 times. That gives me 0.0058 for my answer in standard notation.